Well, welcome back to our two-part presentation on understanding the Student VectorCalculus package. In the first part, last month, we looked at the objects, the vector objects that you can work with, applying differentiation commands and integration commands to those objects. Today, we want to complete that part of the program by looking at what visualization or drawing tools are there, and then essentially some examples and final remarks. So welcome back and thanks for being with us today. So I'd like to give you a summary of the commands that draw pictures. So that's what table 11 does. So we've mentioned the plot vector command. Okay, you get a graph of one or multiple free or rooted vectors, and you can just put them in a list and it takes care of graphing all those arrows. Plot position vector. So that's a special command that plots the position vector, so it draws either the curve or the surface that's been defined as a position vector, and it will allow the superposition of arrows from different vector fields that emanate from the curve or surface. Vector field command. When you define a vector field, you can get its arrows by adding output equals plot. There is a tutor. I showed you where the tutors were. The vector field tutor. So this is the vector field. Now you notice what you see here is a free vector, but under the hood that has to be converted to a vector field. Notice vector field command here. Okay, making this a vector field. An initial point is given. From that initial point, a flow line, a line that flows out along the arrows of the vector field, is drawn. But that's drawn by this flow line command. So this tutor is doing a bunch of things. It's setting the coordinate system, it's defining the vector field, and it's drawing a flow line. And here you can see what the command itself requires. Okay, so vector field, its arrows, a flow line command, it will draw the arrows of a vector field and one or more of its flow lines. So this tutor draws one flow line, but if you use the flow line command, then you can put a multiple of initial points and you can see how the flow of the field itself goes. The space curve command, another one of my favorites. Notice there are two capital letters, the S and the C, because there is a space curve command with all lowercase letters in the plots package. What is the difference? In the VectorCalculus package, the space curve command accepts, using the same syntax, a 2D or a 3D vector that defines the curve. So it's a free vector that defines a curve. Okay. At top level, if you have a true space curve with three components, you use the plots package space curve command, lowercase letters. But if it's in the plane, you have to use the plot command and graph the thing parametrically with a completely different syntax. So the space curve command unifies that syntax and it works with 2 or 3D. That's the kind of thing that I like to see. I'm reminding you here of the space curve tutor. We've seen that. Draws the space curve, puts arrows on it. I might mention here that not only can you get the arrows of the TNB frame, but you get other stuff. You can get a graph of the osculating circles. And I suppose we animate that. And I would do plot options. I would use constraint scaling, and I would put frame. Okay, and you can see that some of these circles are going to get large, right? So that the image is quite distorted, but you can see that you are getting the circles of curvature traversing that curve. That's not the only thing that this command will provide. It will give you a graph of the curvature. All right, you get a graph of the curvature. See, the default range 0 to 2 pi. You want to change that, and you can get a graph of the torsion. Okay, so the line int command. We've mentioned the line int command. We mentioned that it will output a graph. The flux command, it will output a graph if you ask it. And these Frenet-Serret commands will output graphs if you put the appropriate option. Output equals, you can get a plot or an animation. Radius of curvature, you get the circles of curvature, tangent, vector, normal, binormal, TNB frame. I thought it would help if I did at least one example to illustrate how some of this stuff works together. So here's an example, a flux example. Vector field, it's 3 components, so we're in space. Here is the surface, and I'm going to get the flux through that part of the surface that sits over this disk. Disk has center at 1, 2, radius is 1. Now, there is a solution via task template. I showed you there were a bunch of task templates for doing things like flux. Okay, so, well, I better keep some of this information handy. Coordinate system. It's Cartesian, 3 variables, set that system. And you notice as I complete the fields in one section, then another section opens, and that's to force the user, at least for the first time, to go through the insertion of data in an orderly fashion. If this were all open and you jumped around and you put some information in one place and you clicked a button that needed that information but didn't have it, you get all kinds of error messages popping up, and you gotta, it makes the coding very, very hard to figure out what to do if a button has been pressed and it doesn't have the data. This way you have to insert the data in an orderly way. Okay, vector field, x plus y squared, x squared minus y, x, y, z, x space, y space, z, implied multiplication with the space. Then you click continue, and more things open up. The parameters here are x and y. Click continue. X is x, y is y, and z is this thing 10 minus x squared minus y squared. Continue. Now you can put in the disk. H and K, it's 1, 2, right? 1 here, 2 here, radius is 1. Continue. Now you have a place to see what the flux integral is going to look like. There's the flux integral. Notice Maple has converted automatically. The command, flux command, automatically, seeing that as a disk, goes over to the polar coordinates, right? dr and d theta. Now what's the value of that integral? You click here and you get a number, 29 pi over 2. We can also get a solution using the explicit command structure, that'll show you what the task template actually saves you, and will allow a more stepwise insight into how this calculation goes. So initialize, so there's a restart, and I'll just click this single exclamation point. So I'm executing these commands, bring in the student package. Basis format, I like to have my vectors display as column vectors. Then I'm defining the vector field, and you can see the echo back is the column vector structure. So now we can obtain the flux, and we use the flux command. If we say output equals integral, we'll see the unevaluated integral. Okay, so here is the vector field. This is how you define the surface. You define it parametrically with the components in a free vector form: x, y, z of x and y. This is how you tell the command that the integration is over a circle. Should really be disk, but maybe we'll use circle. Okay, in the circle part, you have the center, you have the radius. This part is optional, but it's very valuable. The variables of integration here are needed because while f carries a coordinate system, the circle doesn't. This part of the command will use x and y as an r and a theta, and the integral that's returned will look bizarre because it will be in polar coordinates, but instead of using r and theta, it will be an x and a y. So this optional r theta tells Maple, use r and theta as the polar variables. And here you see output equals integral. So let me execute that. That is the integral that was in the task template. dr d theta is the extra r for the Jacobian. If you do not put output equals integral, then you will get a value immediately, 29 pi over 2. Well, we can dig a little bit deeper and obtain this result from first principles using some commands. Define the surface, z of x and y, use uppercase Z for that. The disk can be represented in polar coordinates, 1 plus r cos theta, 1 plus r sine theta. And then the element of area, d sigma, 1 plus dz dx squared plus dz dy squared. Now there's normally a differential dA at the end of this. It would be either dx dy or dy dx. Maple does not have a concept of differential when it does an integral. It has the integral as part of the integral command. So although I've called this d sigma, it is d sigma less the attached differential dA. All right, let's see what that looks like. Okay, now we need a normal field. In fact, we need a unit normal field, but let's worry about the normal first. A normal to an explicitly given surface, this is an explicitly given surface, a normal to an explicitly given surface can be obtained as the vector minus z sub x minus z sub y 1. If we had an implicit representation of the surface, as we would with this expression, z minus z, then we have all three variables, then the gradient is a normal, and if we normalize that gradient, we would have our unit normal field on the surface. We now need to compute f dot n, the normal component of f dot n, times d sigma, and evaluate this on the surface. So that's why we have z equals uppercase Z. So let's look at that part of the expression. Now to integrate over the disk, we have to change to the coordinates uppercase X, uppercase Y. So we evaluate this to do the substitution. And I'm sure that if we hit this with a simplify, it will become something smaller. But we are now in polar coordinates, so there's the expression Q. R is the Jacobian in polar coordinates, and then the theta dr. This would integrate over the disk, and we would get the same 29 pi over 2. Now there are a couple of final observations I'd like to make. Have to do with scalar fields, then curves, then the directional derivative of a vector field. So let's take a look at scalars. Vectors carry a coordinate system, and the technical term in Maple is that they carry them as an attribute. Points are represented as vectors, so they too carry a coordinate system. But the vector calculus packages made and make no provision for a scalar field to carry a coordinate system, so scalars do not carry a coordinate system. Well, where do you manipulate a scalar field in which the coordinate system might matter? Well, if you take the gradient or the Laplacian of a scalar field, you end up with a vector in the first place and a scalar in the second. So these two commands, gradient and Laplacian, they can take the name of a coordinate system. So you can supply the coordinate system that Maple would otherwise not be able to decipher. However, suppose you want to compute a gradient or a Laplacian in a more natural notation without using those command names. You want to use del on the field, or del squared, the nabla and the nabla squared. How does Maple get the coordinate system of the scalar field? Well, it uses the ambient system. It interprets the scalar to be in the ambient system. Well, if the ambient system is the right system for that field, you're in luck. If the ambient system is not the system that you have defined that field to have, then you have to reset the ambient system with the set coordinates command so that the ambient system provides the coordinates to the scalar field when you compute gradient or Laplacian using this natural notation of del squared. Let me illustrate this issue about scalar fields and their coordinates. Take the gradient, or apply the gradient operator, gradient command, to a function of two variables, just less display by using two variables. You get a correct representation of that gradient vector in Cartesian coordinates, because at the moment we haven't changed coordinates in the background, so the ambient coordinate system is the Cartesian field. If you take the Laplacian, Maple will return the correct result, second with respect to x plus second with respect to y. If you apply the gradient operator to a function of u and v, Maple will interpret u and v as Cartesian coordinates, Cartesian variables, and you will get the gradient vector partial of f with respect to u, partial of f with respect to v. And similarly for the Laplacian, apply the Laplacian to f of u and v, and you get second derivative with respect to u plus a second derivative with respect to v. So Maple is smart enough to pick out these two letters as the appropriate variables. If you would have the gradient operator acting on f of r and theta, well, if Maple treated u and v as Cartesian, what is it going to do to r and theta? Is it going to recognize that those are polar? No, it does not. It treats them as Cartesian, and you get partial f with respect to r, f with respect to theta. This is not the correct gradient if you intended this to be polar coordinates. Same thing with the Laplacian. You will not get the correct result if you intended this to be polar coordinates. Just because you wrote r and theta doesn't mean that Maple sees it as polar coordinates. You get second with respect to r plus a second with respect to theta. That is not the Laplacian in polar coordinates. But you can add the coordinate information as an option to the gradient command, and to the Laplacian command you say polar. And since polar will default to r and theta, you can use r and theta without having to say anything further. You get the correct gradient in polar coordinates, and you get the correct Laplacian in polar coordinates if you include polar. So what's the difficulty? What is the discussion here really? It's about trying to use natural notation, the nabla. So remember, the background coordinate system is Cartesian. If you put del f of x and y Cartesian, you will get the correct gradient. And if del squared f, you will get the correct Laplacian, because the background coordinates are Cartesian, and apparently we're trying to do something in Cartesian coordinates. And even if you put u and v, Maple interprets those as if they were x and y. So you get df du, df dv, you get the correct gradient. And here you would get the correct Laplacian, second with respect to u, second partial with respect to v, added together. If you write r theta, Maple will do the same thing to r and theta that it did with u and v. It will treat them as if they are the Cartesian variables. So you get you get a partial with respect to r, partial with respect to theta. This is not the correct gradient if you intended this to be polar coordinates. But with the nabla, you cannot do this trick of including a system name. Same thing with the Laplacian. If you do del squared f of r and theta, Maple treats r and theta as if they were an x and a y. You get a second with respect to r, second with respect to theta, added together. This is not the Laplacian in polar coordinates if that's what you wanted. So what do you have to do? That's where you need the get coordinate, set coordinate commands. Well, get coordinates will tell you that your ambient system is presently in Cartesian. If you set coordinates to polar, Maple will set the ambient background coordinate system to polar with the default variable names r and theta. Now you can use the nabla, del f of r and theta, and you get the correct gradient in polar coordinates. And if you do del squared f of r and theta, you get the correct expression for the Laplacian in polar coordinates. I've just set the ambient coordinate system back to Cartesian. So this is the one place where you might want to change the background coordinate system, but you have to do very little of that elsewise in the Student VectorCalculus package. You do a lot of that in the VectorCalculus package because there is no such thing as recognized coordinate variable names. So if you look at examples that have been done in vector calculus package, you'll see a lot of use of set and get coordinates, which you do not necessarily find or need in the student package. Some remarks about curves in the student vector calculus package. Okay, so recall that I said the initial version of the packages did not have a position vector or a plot position vector command. So you needed a representation of curves, and they were represented as free vectors. When these two commands were added, they did not change the fact that you could represent a curve as a free vector. So let's take a look at some of the consequences. T squared is a free vector. The about command with a capital A, there is an about command with a lowercase a that's at top level. This is in the package. The about command will tell you information about the object. It says it's a free vector. Its components are t squared. And the coordinate system is Cartesian because the background coordinate system is Cartesian. The space curve command, this is in the package, will act on both a 2-component and a 3-component vector. Draw a graph. The space curve command in the plots package, which has lowercase letters throughout, only works on a 3-component vector. So you have to remember that the 2-component vector has to be plotted with the plot command with different syntax. So here it's uniform space curve command, free vector, and then just some things to make the graph fit into this space better. You will, when the space curve command puts a caption automatically, so not to have the caption print, you do caption equals the empty string space curve command. You can apply the Frenet-Serre formulas. Curvature will act on the curve represented as a free vector because that's how it was done originally, and that's still possible now. So a little bit simplify, assuming t greater than 0, you get a nice expression, and you can compute the principal normal. Another Frenet-Serre command, you can apply it to a curve represented as a free vector. A little bit of simplify, you get a nice result, principal normal. So now let's try representing the curve t squared as a position vector. Notice the square brackets here, but the wedge brackets up here. These square brackets, I think, are mandatory. So you get a column vector as a response, position vector. You can apply the plot position vector command, and something to make it a little smaller. You get a graph of the curve. Plot position vector. The option normal equals true tells the command draw the curve and add, and the default number is 5, normal vectors. And if I were to go to constrained scaling, you'd see more orthogonality in the drawing. Okay, so you begin to see the power of this plot position vector command. Normal equals true is telling Maple draw 5 normal vectors along this curve. If you say tangent equals true, you get tangent vectors drawn along the curve. And the reason why there are 3 of them is because there's this option, vector num equals 3. You can even specify the points at which you want this drawn. I let you look up the syntax of the plot position vector command and see the things you can do. You can put derivative fields, first derivative, second derivative, third derivative field, arbitrary field plot position vector, you can add the option that says draw me arrows from this arbitrary field along the curve. And if the plot position vector, if the position vector command is being used to represent a surface, then you will get arrows of various fields on the surface. Down here we have curvature applied to the position vector representation of the curve, and it works the same way as if we had used a free vector. Here I did principal normal for a position vector representation of the curve, and I got the same result that I got using a free vector. Finally, directional derivative of a vector field. Now, we know coming out of multivariate calculus that you can take the directional derivative of a scalar field. There are two elementary vector identities. This is the gradient of a dot product. This is the curl of a cross product. And if you'll notice, each of these two identities has u dot del acting on v. Here you have v dot del, u dot del, u dot del, v dot del. What are these operators? U dot del, v dot del. How do you apply that to a vector? Well, it turns out that that's a generalization of the idea of a directional derivative, and it's the directional derivative of a vector field. And those, I want to make comments about that in Maple. Now, these next few computations require that we initialize Maple in a certain way, bring in the Student VectorCalculus package. I set basis format to false so that vectors are displayed as column vectors, not as sums of basis vectors. Now I'm going to do some typesetting tricks to make expressions less messy. So I bring in the typesetting package. Now I'm going to be making use of these three functions: f of x, y, z, g of x, y, z, h of x, y, and don't want to have to keep typing all of that stuff out. So I give that sequence of three functions the name q. I apply the suppress command to q, which has the result that f, g, and h will display as the letters f, g, and h, and it will not drag along the arguments. This settings command from the typesetting package, useRep equals true, says display partial derivatives as subscripts. That's really what that does. Now, since q is this sequence of these three functions, if I define a vector f in angle brackets around q, then I've defined a free vector. G is the vector field form of this free vector. Remember, there's a difference between a vector field and a free vector. V, that will be like a direction vector. That's a free vector. U will be its vector field version. And if you want to see F, G, V, and U, F, G, they will display the same. V and U, they will display the same. Now, these next two fields shaded in what on my screen shows up as yellow, they're text. They're not valid Maple syntax. v dot del is the operator, or it stands for the operator, as if you took the dot product of v with a del. So you get u partial with respect to x plus v partial with respect to y plus w partial with respect to z. This partial derivative symbol replaces or stands for d by dx. Even if you tried to use d by dx in Maple, it still would not be valid syntax. So it's just simpler to write this in a less cluttered form. Now, when you apply that operator to a vector, what it means is to apply it to each component. So v dot del applied to the vector f means apply it to each of its three components. So that would be placing this operator, u partial x plus v partial y plus w partial z, in each component acting on FGH. So that would give you u f sub x plus v f sub y plus w f sub z. Here you'd get u g sub x, v gy, w gz, same for h, u hx, v hy, w hz. And if you look at that carefully, you realize you can pull the uvw out as a column vector, and what's left would be these partial derivatives, fx, fy, fz, gx, gy, gz, hx, hy, hc, and this thing is the Jacobian matrix, because the derivatives of the three vectors are all the same in each column. Derivative with respect to x here, this is the derivative with respect to y, derivatives with respect to z. So this operator, v dot del, acting on a vector f, is the directional derivative of the vector f in the direction v, Jacobian v. Let's realize this directional derivative from first principles using Maple. Now, just like you do for a scalar field, you evaluate the object that you want to differentiate along a line in the right correct direction. So we want to form a line. So r is the position vector to an arbitrary point. P is the position vector to a fixed point, and the equation r equals p plus tv, which you see echoed here, xyz equals abc plus tu, tv, tw. That's a line with direction v. But you want to make substitutions into the vector f, so you need equations of the form x equals a plus tu, y equals z equals. So the equate command will do that. And that list of equations I've called C. So then I evaluate the vector f using C to make the substitution. So we get what we wanted, FGH with arguments a plus tu, b plus tv, c plus tw. For a scalar case that you would see in a multivariate calculus course, just look at one of the components. That's what it would look like. Differentiate with respect to t. Well, Maple will use the d operator. The one means derivative with respect to the first argument. The first argument is this thing. Okay. Second argument, third argument. I find that denotation a little bit hard to read. So after I evaluate at t equals 0, that puts me at the point P. I still have these d operators. and I'll do a conversion to the diff operator because I like those better. And you see partial derivative symbols, which make a little bit more sense. But because Maple is when you make this conversion, Maple is looking at these arguments, ABC, so it thinks the variables are ABC. So I want to change those variables back to XYZ, so I just do a brute force substitution. Now I'm looking at something that's beginning to become familiar. Fx, Fy, Fz, UVW, Gx, Gy, Gz, UVW, Hx, Xy, Z, UVW. Okay, what is the Jacobian matrix for the triple FGH? There it is. And if I take the Jacobian matrix and multiply V by the Jacobian matrix, then I get the expression that I computed from first principles for the directional derivative of the vector f of this vector, directional derivative of this vector in the direction v. So from first principles, you can actually do this in Maple. Next, I want to see how you would do it operationally in Maple. Now let's see how you can get the directional derivative of a vector field operationally in Maple. You can see right here that I've overwritten G, and I want to restore the letter G to mean the vector field version of the free vector F. Okay, so I had overwritten it in the previous computation, so I want to make sure I bring it back. If I apply the directional diff command to the vector field in the direction v, I will get the appropriate expression, which we recognize as the Jacobian matrix times v. So that's one way to do that. Use the directional diff command, apply it to a vector field. The direction can be given as a free vector. If you want to get more into the operational sense, and you want to apply the nabla to F, you have to map it onto the components of F. So you map del onto the components of F. And then you need to take a dot product with V, but you have to do that in each component, so you must again map the dot product to the components of what you got when you did map del onto F. So notice that in this formalism, F can be a free vector instead of a vector field, and V can be a free vector. You get what you expect. Finally, if you want u dot del, where u is the vector field version of the direction vector v, if you want to see u dot del acting on the vector, then both u and the vector have to be vector fields, so that G is a vector field, u is a vector field, and you have all these parentheses, u dot del, that groups that together, and it will act on the vector field G, and you'll get what you expect. So you can reproduce u dot del acting on a vector, provided you see these distinctions. This has to be a vector field. This has to be a vector field. The directional diff command will do the same thing, where vector field here, free vector here. And if you want to be completely free vectors, then you would have to do it this way. Map, map. If you now want to take this to a different coordinate system, now you're starting to talk the language of differential geometry, covariant derivative. That's a story for another day.